Right. Well, welcome everyone. It's Monday. Today we're talking about style transfer, style and content. That'll be the lab due not this coming Saturday, but the following Saturday. So again, you have that one extra week to work on lab 4 if you need it. Otherwise, we have a week off. So items of business. Again, we have our weekly readings. Hopefully you're remembering those. Final project, all of the specs are available on Learning Suite. There are 3 checkpoints. First, you have your proposal, then you have your data set, and basically kind of just proof of concept showing that you have access to your data set, you've taken a little bit of a look at it, and then the final turn-in of your project. Between those 3 assignments on Learning Suite, those cover all of the requirements for the final project. So now would probably be a good time to start taking a look at those and yeah, start brainstorming ideas for the final project. Yeah, question? So for the final project, do we need to get good results? No, you do not. You do not need to get good results. In the words of Dr. Wingate, when he taught this class, he would always say, I'd rather have you swing for the fences and miss than go for something easy and not very interesting. The point here is to try to exercise your creativity and come up with something new. And I would even encourage you, try to approach this as if you're approaching a new research topic and trying to write a paper on it. And if you end up, if it ends up being a good idea, you could definitely potentially take this and publish it in a conference. So yeah, Jane.
Do you have any? Do you mind sharing some examples of final projects from past?
We will do that. Not today, but we will definitely take a look at a couple of examples of final projects and maybe give you a more specific idea of kind of what's within scope for this class for sure. All right. Yeah, a couple of things. We're getting a little bit into the semester, and midterms are starting to hit, and classes can be kind of overwhelming. May have had to drop out of class at this point, realizing that maybe you took on bit off more than you could chew. But I can tell you that I've been in that spot before. I've had to withdraw from classes before. There's no shame in that. Yeah, and so just keep in mind there a wider perspective. There is more to life than school, and try to keep balance in your lives. And if you're finding that you're having a hard time balancing those things, the campus has some great resources for academic support and as well as mental health resources. So the slides are posted on Learning Suite. You can get access to those links on there. Yeah, I encourage you to help if you need it and remain optimistic. Failures are short term. They can be overcome, and your life will work out in the long run. So, and also if you're struggling as well, feel free to come and talk to me as well. As far as so review, by way of review, last time we talked about gradient descent, stochastic gradient descent, momentum-based optimizers, and adaptive gradient-based optimizers. So then as a quick review from last time, try turning to the person next to you and seeing if you can remember what is the memory requirement for these 4 different optimizers in terms of M, where M is the memory required for 1 copy of your network release.
Well, I know those from these 3.
So that's I think that just says immediate gradient. That's momentum is 2 gradient. So it's your last one. That's 2. I forget what 8 grad is, but I remember 4.
You mentioned there's the missing one to start looking at.
All right, who wants to take a shot for SPD? What do you think the memory requirement of SPD is? Yeah. 2M. How do you figure? How do you get that? Right. Yeah. Yeah. So that is correct. So SPD is 2M. You have to keep a copy of the weights and then a copy of the gradient of the loss with respect to each weight. And the gradient is one number for each weight, and so that's 2M. Good. How about momentum? You want to take a shot? Yeah, Michael, what do you think? 3M. How do you get that? Yeah, one copy for the weights, one copy for the gradients, and then one copy of your momentum, which is basically kind of a velocity for each of your weights, or a velocity for the gradient with respect to each of your weights, tracking how quickly that weight is changing. Okay, how about attigrad? That was kind of a tricky one. That was the one where we had basically 1 over r squared, or square root of r. Anyone want to be brave and just throw out a number? 4M. Okay, so what do you think, Brendan? How do you get 4M? It's a good shot. So attigrad is 3M, and this is how we get it. We have our weights, we have our gradients, and then we are tracking the squares of our gradients, and that's what our R vector is. So weights, gradients, and squared sum of gradient means that attigrad is 3M. And then finally we have atom, which I guess first of all, atom is a combination of which two approaches? Yeah. Attigrad with momentum, exactly. So that hopefully should give you a clue to how much memory it takes. It's going to take 4M because you're tracking the momentum, the squared gradient. You're tracking the momentum, the squared gradients, the gradients, and your weights. So those will be good things to keep in mind. And there you go. Okay, so today we're talking about style transfer. This is kind of a niche application of deep learning. But I really like that Dr. Wingate chose to include this lab when he created the class in the first place. The reason why is because while the chances of you doing style transfer in the real world in a real job are maybe kind of low, maybe you'll do it. I'm sure there are jobs out there doing something like that. Those caveats aside, this paper and this lab, I think give a really good intuition for what features are, how to design a more interesting loss function, and what the network is learning at each of its layers. So without further ado, we'll hop in. So this is the assignment. We have a starting image, which we will call our content image. And we also have an image in a certain artistic style. And we want to impose this artistic style on the content of this image. And so we can see when we do this, this is the result. We have these same general features of houses in a Northern European style, but with the colors and kind of brush strokes of this target style image. Here's another example: Starry Night. Apply to that same image, and the screen applied to that image. So that is a task. A couple of more examples. Here's the turbo example. So yeah, this is the idea. If you remember, we've talked a lot about lower level coarse grain features and higher level abstract features. And so the intuition here is that we're going to extract the style from the earliest layer, or we're going to have an already trained neural network, and we're going to pass an image through it and extract coarse grain features at the earliest layers, which will represent style. And then we'll take our content image and run it through that same network. And in the later layers of that network, we will extract features representing the content of that image. And then we will create a new image to match the lower level coarse grain style features, as well as the higher level abstract content features. So this is the setup. So you remember taking a look at this VGG network architecture of it a couple of classes ago? This is a 16-layer convolutional neural network, and we have 3 images. Any idea what each of these images might represent based on what we've talked about so far? You have YS, Y hat, and YC. Yeah, what do you think? YS is the target image. Exactly, yeah. So YS is the style image, YC is the content image, Y hat is the image that we want to match both of those. Exactly. So you can see the content, we're going to pass it through this network and extract features pretty late in the network. The style image, we will extract features at each part of the network. And then this designed image, we want to match all of the style representations as well as the content representation. Okay. Yeah, so again, we're taking an already trained VGG network and we are using it to extract features from these images. So this is the diagram of the VGG network. We're not going to worry about these fully connected layers at the end because, again, we're only using this to extract features. And also, when I say features, features are synonymous with activations, and they are distinct from network weights. So when I say extracting features, we're not taking these weights out of the network. We're passing an image through the network and taking the output of one of these layers. Does that make sense? Does it make sense the difference between weights versus features? Raise your hand if you don't know what I mean by weights versus features. A couple people, yeah. You have a question? Good question. So if we go back to our network diagram where we see the circles representing nodes and the lines representing edges, the lines are weights and the circles are activations or features. Yeah, and so the features connect to each other through these learned weighting. Okay. So this is how we're going to do it. We have this VGG network. We'll take a content image, pass it through the network, and take the output of this weight layer in the neural network. take the style image, extract features at 4 or 5 different places throughout the entire network. And again, yeah, there's no learning happening here. These are just forward passes through the network. These networks are already trained. It's the same, we're using the same trained VGG network for our style image and our content, as well as our generated image. So now we're going to take a generated image, and we can pick one of two things. We can initialize it as the content image, or we can just initialize it with random pixels. And we'll get pretty much the same result, though we'll probably get there a little faster if we initialize it with the content image. And as you see, we match the style, the content of this lower image with the style of the above image. Yeah, Travis. Good question. The answer, the easy answer to that is there's a paper that does this, and we use the layer that they use. And they probably did some experimentation and figured out which one best represented those features. Yeah, Drake.
Why is it like very far in that?
That is a great question. Yeah. So Drake said, I thought we were only taking coarse grain features at the earliest layer of the network, but we're taking out features even later in the network than we took the content features from. And you did a great job of catching me and my words there, because we are actually taking not just coarse grain features, but we're going to take features across the entire network. Now the question is, how do we prevent the network from learning content of the style, right? If we're taking these very abstract features out of it. And I will leave you with that question. As we try to answer as we go throughout this lecture. So yeah, how do we prevent the network from learning the content of the style image if we're taking these last style from some of the last layers? So I think this image will start to answer that question. So what we have here is we have 2 input images, and what we've done, what the authors of the paper did is they extracted features at each layer of the neural network, and then they trained a separate neural network to reconstruct the input image from features extracted at that layer. And this is the result. So, this arrow represents a network trained to translate early features back to the original image, to reconstruct the image from those features. This is another separate trained. This arrow is another separate trained network later in the network, and so on and so on and so on. Then similarly, we take style representations at each layer, and we train a network to replicate a separate network for each of these images to translate those features back into the original image. Which of these are you noticing is doing a better job of reconstructing the original? The content reconstructions or the style reconstructions? Probably the content, right? Yeah, these first 4 are almost identical until you basically erase all of the spatial information, right? Yeah, whereas the style is getting kind of these stylistic effects, but is never really able to reconstruct that original image perfectly. And the key here is that our style representations are not, we're not simply taking the features out at that layer. We're going to do something else that's going to be really important, which will answer Drake's question. So this is our overall loss function. Our total loss is a sum of 2 sub-losses, content loss and a style loss, with a weighting between them, alpha, beta. And in fact, you could also just ignore alpha and have a beta, because with your learning rate, you can basically take convert that to like a 1, and then this is just, you just have one parameter to learn, which is, or to tune, which is basically beta over alpha. Yeah, and that ratio, alpha over beta, was either what was around 0.001 or 0.0001. So the content is being, let's see, if alpha over beta is low, then we're heavily emphasizing the style and not putting very much emphasis at all on content, at least as far as absolute loss goes. So what do these things represent? P is our content image, A is our style image, and X is the generated image. And so the content loss will be a function of the generated image and the content image. Style loss will be a function of the generated image and the style image. So this is our content loss. We're going to take these two matrices, FL and PL. FL are the features of the generated image at layer L. And PL, can you guess what those are? The features of the content image at layer L. Yep, and then we're summing over I and J. So yeah, here's a quick question actually. If we're going to extract the activations at layer L of a convolutional neural network, how many dimensions will those activations have? Will it be a 2-dimensional tensor, a 3-dimensional tensor, 4-dimensional tensor? I'm seeing a 3. What would those 3 dimensions represent? Height, width, and depth for number of filters. Great, that is exactly right. So yeah, that will be a 3-dimensional tensor, but here we're only summing over 2 dimensions. The reason why that is because we are basically taking our height and width and flattening them out into one long vector. But we could equivalently just say we're summing over I, J, K, where J and K represent the 2 spatial dimensions. They're the same thing because we're just taking a sum over all of these to get a loss. Does that make sense? So I represents the number of filters, and J represents the height and width spatial dimensions that we're summing over. Yeah, question. Good question. So the question is whether for the content images we will include color or whether that will be consumed in the style. We are going to pass in color content images, but we will see a little later how you can basically make it so that no color comes at all from your content image, which is a different paper, but kind of interesting. Yeah, I saw another question. Okay, great. Okay, so then, yeah, we take the outputs of this layer, which this will be layer 8. NL, the number of filters, is 512. ML is 28 times 28, 784. And so FL will be a 512 by 784 matrix of filter responses or activations or features with each row of that matrix being one filter stretched out into a vector. Okay? Now, this to me is the really ingenious part of how this paper approaches style transfer. So the style loss function is a little bit different. One second. An equation is not showing up. And just gonna do a quick rearranging of slides here. Don't mind me. Okay, as we were. So the style loss function is going to be a function of the gram matrix of the features at that layer. So we still have the same feature matrix, but we are going to compute the gram matrix of that feature matrix. And what that looks like is multiplying that feature matrix with the transpose of itself. And I will show you what that looks like. So we take the activations at this level. Again, they will be 512 by 784, where 512 represents the number of filters and 784 represent all of the spatial dimensions. Now the gram matrix is a 512 by 512 matrix of filter correlations. So if you remember, what does a dot product represent? Similarity. And if we take the transpose of a matrix and multiply it by itself, the output matrix will be the dot product of each of the rows in that matrix with all of the other rows in that matrix. And we call that the gram matrix. Now think for a second, why might it be useful to compute the correlation of different features for your style representation? Hey, what do you think? Yeah, so the idea is that you want to compute style across the entire picture. That is definitely a big part of this. So yeah, so what you just pointed out is the fact that we have just erased, by computing the gram matrix of those features, we have erased all spatial information that we have. Because if you remember, the spatial information was contained in the columns of that feature matrix. So the rows represented different filters or features, and the columns represented where in the image those features were. By taking the gram matrix, we erase all of the spatial information and we're only left with the correlation of features with themselves. So that's where the whole image comes in. No more spatial information. And why do you think the correlation of or similarity of features with other features would be helpful for style? Yeah.
A lot of times certain things so like when you write your condition, you know, okay, do a swish, they also park their eye, okay, so the switch, there likely is like a heart at the top, or like right, and the key is that a lot of those
Totally. And so you can think of a style as being composed of kind of intersections of various features. And so that's the intuition for our style representation, is we're looking at the correlation of stylistic features that we're getting from the gram matrix of the features. Any questions on this? Okay, so our loss function will look very similar to our content loss function, only we are taking the gram matrix of our style image and the gram matrix of our generated image, and we're taking the the mean squared error across all entries of those matrices. And then, yeah, this dividing by n squared is to normalize for feature maps of different sizes. Oh, and also there are our final style loss. Our content loss only comes from one layer, whereas our style loss comes across multiple layers. So we will also sum across several layers with different weights for each layer. So if we can go back to Drake's question of why do you think that we are, why do we not get content out of the last layers of this style network? Why do you think that is? Now that knowing what you now know about our style representations and our content representations, why are we still getting style out of the last layers of this network instead of content? Yeah, Brandon, what do you think? Exactly. Yeah. So yeah, couldn't have said it better. Taking the dot product matrix or the gram matrix of our style means that we've destroyed all spatial information, and all we're left with is the correlation of different features with each other. And so that's why we're not seeing strong style content in the last layers of that network. I'm not sure I said that right. That is why we are not seeing content information in the even taking features from the last layer of the network. Okay, and then this just sums up what we just said. This is a line from the paper. Why are we matching features for content and feature correlations for style? It's because this creates images that match the style of a given image on an increasing scale while discarding information of the global arrangements. Okay, so specifically the layers we use are comp 11, 21, 31, 41, and 51 for the style features, and then comp 42 for the content information. So this is an interesting visualization. The rows represent the layer at the VGG in the VGG network, and the columns represent the ratio of style to content. So you can see that as we go across the rows, we go from more abstract style to more content. And as we go from top to bottom, we have very coarse style. This top left image should remind you of the style features that we saw at the first layer for Starry Night. The very just little dots of color. Whereas as to the bottom, our style becomes higher level brush strokes and things like that. Oh yeah. So
okay, probably we're saying that like the two different components are taking the
correct. Yeah.
that's
So
because we look at the activation all the time.
yeah. So we match the content at only one layer, and we match the style across several layers. And I think a good explanation for that is, you remember in the earlier image when we were looking at the reconstruction, the content reconstruction for each of the layers was pretty much the same, right?
Yeah.
Whereas the style was changing quite a bit from the earliest layers to the late layers.
Yeah.
And so I think that's why we are matching only one content layer and various style.
Like the cost function will tell us stuff.
Exactly.
Okay. So
Yeah. Hey. So we talked about our loss function, but we already have trained networks what are we optimizing then? What are we changing? How is this working? And I don't expect you to know the answer to that because I haven't told you, but the answer is instead of tweaking our network weights, we are tweaking our input image. So remember how a neural network is f of w and x, where w are the weights and x is your data? Well, here we are flipping the learning problem. Instead of learning weights to learn a function between x and y, we are taking weights and freezing them and tweaking x to maximize our loss function or minimize our loss function. So yeah, so do you think that would take longer or shorter than a single forward pass that would predict a style transfer image from an original image? The algorithm that I just described, where we're optimizing over the weights of the input. You think that would take longer or shorter than a single forward pass? Yeah? Exactly. Yeah. So, but in both cases where we would be using we have a forward pass through a network, but for style transfer, for every update of our input image, that's a gradient descent step. And so a single forward pass will be much faster than this style transfer algorithm that we described, where we do a forward pass, then gradient descent on the input image, forward pass, gradient descent again, until we've minimized that style and content loss. Yeah, Travis. Yeah, great question. What do you think the networks originally were trained on? What do you guys think? What would work for what we're using this network for? What do you think?
Image classification.
Image classification? Yeah, that would probably help. Yeah, because we're trying to learn a feature extractor, right? That's what we're using our network as, right? We're using it as a differentiable feature extractor. So image classification might work. What other kinds of training tasks might be helpful to learn these features? You say pixel to pixel? Yeah, pixel to pixel. Yeah, image segmentation could be one. Yeah, object detection. Yeah, so you can imagine any number of tasks that this VGG network could have been pre-trained on, which would have been helpful for extracting these style and content features. Yeah, it's a good question. So the question is whether the data set that this VGG network that was trained on, does that matter for our style and content extraction? Like, what if it didn't have any buildings in it in the training set? That might be an issue, but I'm kind of inclined to think that it wouldn't be an issue because neural networks are really good at kind of bootstrapping learning by using things that it's learned for one task on other tasks. And so you can imagine if there was anything in that data set that had boxes, the neural network would probably get pretty good at recognizing edges and depth and things like that. And so, and that might help with building. So it might matter, but I think for our purposes of feature extraction, it might not matter as much as you think. Yeah, Olivia. Yes, yeah. So the image that we're optimizing is we could either do a random initialization of that image or initialize it with the content image. Yeah, that was our y hat that you saw originally. Okay, so now we're going to take a look at a couple of variations. this is a real-time style transfer. So we talked about how long this process would take. We have an entire optimization process just to make a single image. You can imagine that that doesn't work for if we want to style transfer an entire video. So we're going to do something different here. You know, we're not getting audio, so I'm just going to, we're going to just go through some slides that explain how these things actually work. I think that would be more useful. So, here we're going to look at a couple of variations of style transfer. So one option is going to be spatial control, which is where we control style transfer for one region of the image. We're going to do one which is color control, where we only take color from the style image, and then another, or where we transfer no color from the style image, and then another where we do some scale, where we control for scale. So yeah, color control allows us to operate on luminance or lighting and color independently. Spatial control will allow us to tune style transfer for certain regions of the image. And then scale control will allow us to blend different combinations of low and high level features. Okay, so this is spatial control. So we have a content image, and we have two different style images, and we want to apply the style 1 to one region of this image and style 2 to a different region of the image. So this is what you get if you use the normal style transfer that we have already looked at. And you notice that we're kind of seeing these ghost towers in the sky, which seem to be reminiscent of style 1. However, with spatial control, we only apply this, we basically draw regions around the border of the house, and say we want to transfer this sky pattern to the region above the house and the building pattern to the image of the house itself. And you can see this a little better. Now this last one, we combine style 2 and style 1 and say we want to apply the sky from style 2 to the sky of this image, and the house style from style 1 to the house. And you can see you kind of have a nice boundary there where you're getting the sky in the style of style 2 and the house in the style of style 1. Yeah.
That boundary.
Good question. So I actually have not read this paper, so I don't know the exact algorithm that they use to do it. But it looks like they are in the top right corner of each of these images. You can see that we're provided a segmentation of that. And I think that definitely plays into it. Okay, this is the luminance and color one. So we have a content image, we have a style image. This is what happens if we transfer the style using our normal algorithm, and you can see that the house gets very saturated with blue and you can barely even see it anymore. So we might want to do something different. So this one preserves all of the colors of the original image, but transfers the luminance or the lighting of this image. And so you see these kind of ghost lights showing up throughout that image. This one preserves, I'm actually not sure. So I believe this might have provided a certain color palette or histogram that we wanted the style transferred image to match. Okay, and then we'll skip that for now. So we talked about the difficult, like how long this optimization process takes. What if we want to do this faster? What if we just train a neural network to translate directly from features to a style transfer image? This is how we do it. So we have we generate our target image for our new neural network in the same way that we did originally. We do style transfer, and that entire optimization process produces this target style image. Now, then we take that target and we train a neural network to start with an input image, to start with our original image, and transfer our original content image and do style transfer directly to that image. Does that make sense? So now how long does it take to produce an image? If we have this trained network, a single forward pass, right? Goes directly from image to style transferred image. Those are just some of the training details, and the result is basically equivalent in quality to the original Gaddis paper that we're based on, but does it much faster enough for real-time style transfer on video. And these are just a couple more examples. And that is where we will end for today.